So this entire topic comes from the idea that can two percussion instruments communicate with each other without really having the intricate knowledge of the patterns and the language. So the two instruments that I've chosen here today are tabla and a drum kit. And just to give a background, tabla is really known for its complex and expressive rhythms. And this talk introduces a system that can not only notate the tabla performances, it classifies each stroke using machine learning algorithms, and then responds with a drum groove that can follow the original rhythm. So just to tell a little bit, so the tabla is a North Indian percussion instrument which has basically two pieces. One is the smaller piece, the other one is the bigger piece. The bigger piece is usually the low end and the higher piece is mid to low higher frequency. And the construction of like the body is made out of the copper or terracotta usually, and the top part is made out of goat skin. The black thing that you're seeing is called siyahi, that is basically a tuning paste. And it depends on where you hit on the tabla that gives the harmonics to each timbre, like each hit. And for teaching purposes and for performance purposes, each of these hits have been given names. And that is the vocabulary of tabla. So like, for example, if I'm saying dha, dhin, dhin, da, which is like the vocabulary, that is how the hits are played on the tabla. So where is the motivation coming from all of this? So in Indian performances, one of the main concepts of making it interactive between two performers is something called as jugalbandi, which means that if I, for example, if I say, for example, if we're just talking about synonyms of table is a bad example, of fruits. So if I say apple, you say mango or something. So it's basically call and response. And the idea is, if a drummer does not know tabla patterns, can they still converse? The answer is yes, intuitively. But my thing was, right now, you can converse it as a drummer, or you can converse knowing the tabla patterns. So for me, the intuitive, like the most instinctive thing was, is it a language barrier? Like from English to French, French to English. And there is one person's video that really inspired me, Paul Westfold. He basically does a manual translation of tabla rhythms into drums, to give an idea. So yeah, this is where the entire inspiration comes from, because he's speaking the Indian rhythm, which is played on tabla, but playing it on drums. So the idea was like, if I give the system a tabla pattern, can it give me the response in drums? This is where the inspiration comes from. So what kind of a system am I trying to build? A system that listens to what's coming in, then understands the notes and also the swing or the timing, and then translates it into the drum language, and then hopefully respond with variations. So there are three problems that I put together. The first is classification, which is like, if the system hears multiple tabla notes, can it detect which note is coming in? Second is timing. Can we get the swing representation of whatever is coming in? The third is the generation challenge. So just to give an idea, because it's a hand-played instrument, even though so these are 4 spectrograms for 2 notes, and they're just slightly different, which means that even no matter how amazingly trained the tabla player is, because it's hand played, there's going to be variability. So for classification, just to give an idea of the data set, I used for 8,408 strokes, and out of which some of them are self-recorded by my friend Vaibhav Vijay, and the other ones are collected from Kaggle dataset. And these all notes are broadly basically put into 12 classes. And then there are way more, to be honest, like there are at least 15 to 20 or something. However, just to keep it neat, I initially, and to begin with, I started with 12 classes, which can be broadly put into 3 categories. So there are ringing strokes, then there are bass strokes, and then there are closed crisp strokes. And for the generation, what I'm using is 248 sequences, or between 4 different kind of tals. Tal is basically a term used to describe a beat loop. And there are 4 different kinds. There is 16-beat loop, 12-beat loop, 10-beat loop, and 7-beat loop. So the data set is imbalanced, which is because some notes are more likely to come in the playability than the others. However, this did not make much of a difference while doing the classification, because I did a weighted distribution and one non-weighted, and it didn't really make too much of a difference. So just to brush over the feature extraction and the architecture. So it started with RCD because it works really well for percussive instruments. And then the second is, which I think really gave the classification its niche, was using MFCCs and chroma. The interesting part is that tabla is not only a timbral instrument, it is also a pitched instrument. Like we usually, when singers are performing, the tabla players who are accompanying them, they match it to the scale that they're performing with. So so over here in the data set, I not only have tabla hits from one pitch, they are from different pitches, which means that this is purely a timbral problem. It is like the pitch is not taken in the consideration. And then for the pre-processing, we have the 0 padding to 72,000 samples because that was the longest hit. And then I did the normalization and the feature stacking. And to give an overview, I got the validation accuracy of 97%, which was something that I'm happy about. And the training time was 2 hours, and it was done on CPU. So out of all of this, the main thing to notice was that the errors that I got were systematic errors, which means that the errors were within each category. So like key cut, they both belong to the closed crisp category, which means that we can do something about it because it's systematic and not just unpredictable. And I'll come to that later. But to give an example of how the classification happened, so this is one of the beat loops, 10-beat loop. And you can see in the table, there is the actual notes that should be predicted and the predicted ones. And then there's the drum notation. That is the tabla pattern, and then the drum pattern. So this is how the tabla was classified into drums. And to give another example, and then the drum kit. Sorry, I messed up the other way around. Yeah, but yeah. So you get an idea that it's been able to classify it. And then the second question, which probably is the closest to my heart, is can we capture the human performance and the swing timeline, basically, rather than having a fixed grid, make a grid based on what's coming in. And to look at it, I have 2 levels of looking at it. One is the macro level and the micro level. So macro level looks at the beat level of the groove, and the micro is the subdivision patterns. So, sorry. Yeah, sorry. Yeah, so basically, over here, I have a system. I can talk more about it in detail because that was my entire master's project. But the idea is that once there is a system that's coming in using a system that's in place, you can calculate the like the swing ratio. So you get like what's the distance between each of the beats. And that gives you the amount of swing ratio on a broader level. And in the micro level, like for example, in some of the grooves, it's like dhin, dhin, dha, ge, tere, kit, which means that some of the beats have two notes happening in the same beat. So they're the subdivision, which means that it makes duration bends, like whether it's the short duration bends, where it's like 1/4 of the beat or half of the beat. So it looks at the duration bends of each of the notes. And that's how it creates the swing timeline. And yeah, sorry. Yeah, so I'm using the LSTM model for the prediction of the next likely note. To give an idea of what the LSTM model is, it's a type of a neural network that helps and is designed for sequences. And music is sequential. Like, given the fifth note, like 5-note phrase, what's the next note? And the idea here is that it is able to capture the context of the tabla player, whatever the input is given in. So in this architecture, it's predicting the notes as well as the duration bends. But the interesting part is, given what the input is coming in, it first detects what's the meter that's coming in. So if the meter is 12, then it is, so the LSTM is conditional on what meter is coming in. Because initially I didn't do that, and the output was a little bit too out of hands. So just to make it more musically intuitive, it makes sense to keep it within the realm of what the input is given. And the second point is embedding regularization, which takes us back to the systematic errors. Because there are systematic errors, in the prediction of what I've done is that the notes which are within each category, they should stay close to each other, or they are replaceable, basically. And as I mentioned before, the training is 248 sequences, and it is not like the ideal data set in the sense that I need to have way more of a data set. However, it's good to work as a proof of concept. And yeah, to give an idea, like the overall architecture, so it starts with the input layer of tabla. Then you have the intelligence layer, which basically detects the meter, the swing, and the groove. The third layer is the generation layer, which is your LSTM, which detects what's the next. And then the blending layer, which I'm going to talk the next. And then I have added a bit of musicality in the drums when they're coming out, because just to make it more musical. And then the output. So to give example over here, let me play it one by one. Okay, that was a bit loud, but yeah, that is the input, for example. And then the exact translation in drums would be. So yeah, this is basically an exact translation. However, if I had to do like the output, which is basically not the best, but getting there. And the idea is that there is the different levels of variation that I wanted the AI to add, because I was like, I don't want it to be like, even though it's following all these rules, I want the performer or like whoever is using this to have a capability to add how much variation do you need from the previous one. from the input. So sorry, not able to play it. Sorry, multiple files started playing, my bad, I'm so sorry. But yeah, the idea is that it basically is a blending knob between what's coming in and what the AI is generating. So this is another example. We'll do it quick. So this is in tabla, and drums would be. So yeah, this is the example. And if I have to look into the improvised output, sorry, yeah. So basically, you get the I can share more about it, but the idea is that it allows the generation to happen, and then it gives the user a capability to blend with the amount of variability that you get in. And to just do the last slide, the conclusion is basically I started with 3 questions. Can we capture the timbral vocabulary to a certain extent? Yes. Second, can we capture the swing template? Yes. And then the third one is can the AI respond keeping the groove intact? It has been able to keep the groove intact, but I'm still working on making it more musical for tabla players to interact with it in the real time. And then the next steps for me ideally is right now what it does is it gives me a real time feedback. Like if I give it a phrase, it gives me a response on a phrase-to-phrase level basis, but I would ideally like it to be on a real-time stroke-to-stroke basis. So I need to make it like more low latency and faster. And from a research point of view, I was thinking like the left hand has a lot of bend in the tabla. So it allows you to basically, if I can capture that bend, I can basically use it for physical modeling and for other instrument synthesis bit, which can be very interesting. And secondly, the idea is that right now, what is happening is that I'm kind of prompting drummer to play like tabla player. But this can also be done with Google Magenta, where if you give it the MIDI, it plays how a drummer would. So it is a choice. Like if you want it to respond like a drummer, then it's that, and yeah. So basically that, and yeah. Thanks. Thank you so much.